This is Chapter 3, Kinematics in Two Directions and Vectors. So in this chapter I will formally introduce vectors and scalars and talk about how we add them, a couple of graphical methods. We'll talk about subtraction of vectors and multiplication of vectors by a scalar. We'll talk about another method of adding vectors, which is using the components, and more importantly, how this applies to motion in two dimensions, which will be covered in projectile motion. We'll talk about solving projectile motion problems and how the motion is parabolic, and we'll end with relative velocity, which is very similar to the relative position that I discussed last chapter. Now, as I mentioned last time, there are vectors and there are scalars. Now, a vector has magnitude and direction, while a scalar only has magnitude. Examples of vector qualities: we've discussed position, we've discussed velocity, and we've discussed acceleration. Other vector quantities might be something like force. If you're pulling up, that's a big difference as opposed to pulling down on something. Now, a scalar only has a magnitude. Examples of that we've already discussed. We've talked about speed, we've talked about distance. We could also say examples would be temperature. We could talk about how mass doesn't have a direction. We could talk about maybe even your blood alcohol content. It doesn't have a direction, it only has a magnitude. Now, with a vector, we tend to draw it with an arrow. So I'm drawing this car's velocity as it goes around the turn, and we can see the velocity is changing. Again, that means that it is accelerating. Now, a perfect example of this in your everyday life is, suppose you and your friend are, sitting at the side of the road, and your friend says, "Hey, look, that car is going 25 miles per hour." And you say, "Wow, that's pretty cool." And then your friend says, "That car is going 25 miles per hour directly towards you." All of a sudden, you start to care about that a little more, huh? And that extra piece of information, the direction, makes a big impact on what you're going to do. Now, adding vectors, we did that kind of conceptually last time. I'm just going to go over it again here. Suppose we're looking at vectors in one direction and you want to add some vectors together. And if you travel, say, maybe 4 kilometers to the east, so we're talking about your position, and then you go ahead and you travel maybe 2 more kilometers to the east, then your resultant vector the resultant vector is x2 plus x1, and logically that would say that's going to be 6 kilometers to the east. Now, we can also subtract things, much like we did last time, where if we say, okay, we're going to travel 4 kilometers east, and then we're going to come back 2 kilometers to the west, then the resultant vector, shown by this red guy right here, is going to be x1 minus x2, or 2 kilometers to the east. So we do need to be careful about the signs of the vectors. Are they going to the east? Are they going to the west? Are they going up? Are they going down? definitely need to pay attention to that. Now, if the motion is in 2 dimensions, then it's a little bit more complicated, but it's kind of the same. Now, if we consider a displacement that initially goes maybe 10 kilometers to the east, and then we say, hey, you know what, you turn and you walk 1, 2, 3, 4 kilometers north. We can actually add these 2 vectors together to describe your final position from your origin. And we would write that resultant vector just like that. Now, the distance that you traveled, we can use the Pythagorean theorem to do that. We can say that the magnitude of the distance traveled squared is equal to the magnitude of distance 1 squared plus the magnitude of distance 2 squared. Now, lastly, multiplication of vector by a scalar. We can multiply any vector by a scalar such that we would write it like that. And if I simply wrote v1 to look like that, and if I said now v2 is equal to twice v1, then v2 would be twice the length of v1, pointing in the same exact direction. If I said v2 is equal to negative 1/2 v1, then I can kind of treat these 2 guys separately. The negative says that it's in the opposite direction, and then the scale factor, the growth factor, or the shrink factor, is the 0.5. So this says v2 is half the length of v1 and in the opposite direction. Now, this is very, very, very important, adding vectors by components, or maybe more importantly for what we're going to do, breaking a vector down into its components that are convenient for us to analyze. So if I have a vector, and I'm going to call that vector v, and it points off towards the northeast, then I could also write that vector as the sum of 2 other vectors, a vector that travels along the x-axis and a vector that travels along the y-axis, vy. So now I could write the vector v as the sum of vector vx and the sum of vector vy. And again, the length of v is going to be the square root of vx squared plus vy squared, Pythagorean theorem. Now, we typically choose our vectors such that they fall along the x and y axes because that makes them easy to work with. We're familiar with north, south, east, west, and positive x, positive y. And we choose them to be perpendicular such that we can write our vector v as the sum of those other 2 and use trigonometry to calculate the angle and the relative lengths. So if you remember from your trig classes, SOHCAHTOA, where the sine of an angle is equal to the opposite divided by the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. If I define my angle right here, theta, then the opposite is going to be Vx, the hypotenuse will be v, and the adjacent will be vx. So sine of theta is again going to be the opposite vy divided by the hypotenuse v, and we could write our vector vy to be equal to our vector v times sine theta. Now we do the same for the co and the toa, and last but not least we have the magnitude of v written as such. Now we can add two vectors by components as well. Here I'm showing the tip-to-tail method for adding v1 plus v2, and if I were to break v1 up into its two components, v1x and v1y, and now I look at my vector v2 and I write that as v2x and v2y, where I've simply broken each vector up into its respective components. Now if I look just in the x direction, v2x, and I add v1y down here, then my resulting vector can be written as v1x plus v2x plus v1y plus v2y. I can add the components of the vectors along the x and y axis and come up with the resultant vector. Now when you're adding vectors by components, first thing you do is just draw a diagram. Say I've got two vectors, v1 and some other vector, v2, and get kind of a feeling for where you think the sum of the vectors should be. So draw a little diagram, get a feeling for what you expect. Choose your x and y axes, and in this case it's easiest to choose them like that. However, if these vectors were both rotated by a certain angle, then it may make more sense to choose our axes to look like that, such that one of the vectors lines up on the axes. Resolve each vector into x and y components. Calculate them using sines and cosines like I showed you on 2 slides ago. Add the components in each direction and find the length. And we could use the TOA, the tangent is equal to opposite divided by adjacent, to get the angle between them, where we would take the inverse tangent of vy divided by vx.